Okay, so today in this lecture we are going to study some properties of dynamical systems like the Lyapunov exponents. Uh, Taking the example of 1D maps, for example, the logistic map that we have been studied, or the tent map, we shall get to it. So essentially, we are going to quantify chaos, or what do we mean by chaos? So for example, we have seen in the logistic map, you have the parameter Rn that, as we saw, gives the value of R, where the 2 to the power of nth cycle occurs or appears. So for example, R1 was at 3, where the first period doubling occurred. R2 was 3.449, where this guy occurred, so on, and let's just say R5 was 3.568759. 2 to the power of fifth cycle occurs, and that was the limit R infinity, where the period doubling occurs and you get in period infinity orbit. And we ask the question, what happens beyond R infinity? So certainly we don't have a trajectory settling on a periodic attractor. There's no stable periodic attractor. But what is a guarantee that we can call the system as chaotic? So the question can be, does this aperiodicity imply chaos? So chaos is a very interesting and a very special thing. To be called chaotic, it's a property of a dynamical system. To be called chaotic, aperiodicity is not enough. A system should show sensitive dependence on initial conditions. Neighboring trajectories, by trajectory I mean it can be a map where the trajectory is a set of discrete points, or a flow where the trajectory is continuous, but neighboring trajectories spread exponentially fast from each other, spread exponentially fast, of course, away from each other. initially. So these are the two trajectories. I start at x0 and a trajectory very close to each other. The rate of separation of these trajectories is exponentially fast. We're going to quantify this spread. So lambda n, the separation, would be given by some time. So this is a continuous system, so this would be given. The spread is going to be exponentially fast by some rate. So, of course, since this is a bounded system, these trajectories are going to be exponentially fast and they'll again come back near each other, then go away. So, when I say the trajectories are going exponentially away from each other, this is the initial thing. Divergence of trajectories initially is going to be exponentially fast, and they are going to again come back because the system is going to twist and fold and then they reach somewhere. So this is just a Poincare section of a n-dimensional map. These trajectories may be in 3-dimension or higher dimensions, but that's essentially what's happening. So exponential separation of trajectories initially. So how do we quantify this thing? Let's say, take the example of discrete maps. So I have, let's say, two trajectories, and I iterate them to n time steps. This becomes this guy, and this is what my separation looks like. Now time is discrete, so this is time, or how many times I am iterating the map. This guy, which can be expressed as 1 over n logarithm of this guy. So I'm just taking the log of both the sides and expressing the coefficient or the constant lambda, which quantified the rate of separation of trajectories. Now I can write this formula as so what was lambda n? Del n. This was nothing but quantifying the errors this guy, right? That's what lambda was. So I'm just writing, remember f as an aside, this is a map applied to an initial condition, that is, this is applied n times of the iterate. So that's what I mean by f of n. So when I am computing xn or xn plus delta n, I mean I am iterating the map f n times some initial condition. Let me call it this way. So as the initial separation goes to 0, in the limit, let's say delta goes to 0, this guy becomes the derivative. So I get 1 over n logarithm of the derivative of the nth iteration of the map about x0, and that's what gives me the Lyapunov exponents. And well, so I can apply the chain rule. I need the derivative over here of this guy And the chain rule is going to yield the derivatives along all the iterates of the map. You can check that. That's basically the chain rule being of differentiation applied over here. So that is cool, because now I can write this as a sum of I goes from 0 to n minus 1, and the consequence of the sum are I want to take the derivative at all the points of the map. So this was f1, this would be f of x0, this would be f of x0. So all the iterates, and I have to take the derivative across these points. So this would be giving me x0, this would be giving me x1, this would be giving me x2, so on till n minus 1, x of n minus 1. So that is how I quantify the Lyapunov exponent of the system. And I just write it out here, where xi is x1, x2, xn minus 1, and xi is nothing but ith iterate of the map applied to the initial conditions. And usually, as far as Lyapunov exponents are concerned, we are interested in the long time average behavior of this thing. So lambda is given by limit n goes to infinity, summation over the derivative logarithm of the derivative of the map at all points visited by the trajectory of the map. That's the Lyapunov exponent of the system. So now, thing to keep in mind is that in general, the way, of course, a lot of these calculations are done numerically, but the way one calculates Lyapunov exponent two things need to be kept in mind. So such a calculation in general for finite n, we won't iterate to infinite n, would depend upon initial conditions. That is x0. But to avoid that, we ignore the transient behavior. So we ignore the transient behavior and allow the trajectory to settle on an attractor. Ignore the transient behavior. Allow the trajectory to settle on a particular attractor. So for that, we ignore the first, let's say, L iterations. Well, this would be f of x0, so f of L of x0. So we ignore the transient behavior. Which allows the trajectory to settle on an attractor and then perform the calculation. So when that happens, I get the lambda. So lambda was this guy, and for chaotic systems, lambda is greater than 0. Remember, lambda was capturing the rate at which these trajectories were going away from each other. So a positive exponent means indeed an exponential separation. So that's chaotic systems, and lambda is 0 for stable fixed points, periodic or stable periodic orbits, so on and so forth, limit cycles. So on and so forth. So, for example, let's consider the logistic map. Xn plus 1 equals to 1 minus xn. And the p cycle, let's calculate the Lyapunov exponents around, or the period p orbit. So notice a period p orbit essentially means that a map applied, a new map, which is the initial map applied p times. This is a fixed point of that particular map. So by plugging in the expression for the Lyapunov exponents, I get sum over the derivatives of all the iterates, logarithm of them. And since, of course, I'm taking it to be n to the infinity, but you notice that this trajectory for infinite number of times beep, 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 beep is going to basically hover around these p stable points. So I'll get the same p terms in this derivative. So I can write it as these guys. I get the same p terms. Keep appearing. The same p terms keep appearing. And what do I get? I get 1 over p log of this guy Remember, the sum of the logarithm is actually the chain rule product, and that would be the map FP derivative over here. So in other words, the derivative over here, that is going to be nothing but x1, x2, f, x3, so on and so forth. So what do I get? I get this guy. Now this guy is less than 1. Why am I asked? Because remember, this was a stable fixed point of Fp, or in other words, a stable period P orbit. Remember how the period doubling occurs? This thing will lose stability and then period doubling will occur. But why this exists, period P orbit, this is a stable orbit with this particular condition. So I get lambda 0, lambda less than 0, because this guy was less than 1, logarithm of something less than 1 was 0. So this is an example of a system which is not chaotic. Of course, we already know that because the trajectory was stable around this fixed point. We can consider another example. In fact, another class of maps which is much easier to uh, explore than the logistic map, or another 1D map, which is the tent map. So the tent map is, consider the tent map. Defined by Rx if x is between 0 and half, and R minus Rx, which is basically when x is between half and 1. So this is a map defined for R between the values 0 and 2, and x would be, this would be the range of x. So sketching the map, basically this is the iterate, and this is what you're going to get, R by 2. So the nice thing about the tent map is that f dash x, which is useful in calculating Lyapunov exponent, that's plus minus r for all x. And the Lyapunov exponent would be given by these guys, and that's essentially logarithm of r. So for parameter values r greater than 1, lambda is greater than 0, and this map is going to be chaotic. So depending upon the shape of the tent map, if the tent map becomes narrow, that leads to the map getting chaotic. So this would be the condition for chaos. So in general, so these were the examples where we were able to make some analytical progress in calculating Lyapunov exponents. In general, these things are explored numerically. You have to rely on MATLAB or Mathematica to calculate the Lyapunov exponents. Thank you.